Hello all, welcome to the new video of Signals and Systems. So few months back I had made few videos on transmission line equations concepts, and it dealt with how to find the transmission line equations and how to derive the characteristic impedance. So this video, the third in the series, will continue from where we had left. So in this video, initially we'll build a foundation on transmission line. So first we'll see how to derive the impedance at any point on the transmission line, and then we'll see few characteristics, and then eventually we'll see how the quarter wave transformer works. So before we go to quarter wave transformer, it is very important for us, for all of us, to understand the transmission line equations, how to find what is the impedance at any point and what happens, and what is impedance matching and how important is impedance matching. So those all things. Okay, so by now I'm sure all of you are comfortable with what is a forward wave and when what is a reflected wave. So if impedance is not matched, then what happens? There will be a reflected wave. So we cannot fully send the total full power to the load. So those are all things which are the basics. Okay, so in this video, let's start with the how to derive uh, impedance at any point on transmission line. At any point of transmission line. So let's see that. Okay, then eventually we'll go to quarter wave transformer working. So these are the basic transmission line equations which we had derived in the first video lecture. So this is V is equal to V plus e raised to minus gamma x plus V minus e raised to gamma x. So the first term on the RHS, that is right hand side, is the forward wave, and this is the reflected wave. Okay, and this is the corresponding current equation. So now we are interested in finding out the impedance at any point on transmission line. So these are our basic equations. Now while we are trying to find out the impedance at any point on transmission line, so it is very important for us to use proper notations. So at any point means where exactly? So that's where we need to introduce the new notation. Okay, so this is the typical transmission line. So as you can see, there is a generator connected at a dash, and this is a transmission line. So this generator is sending a signal through this transmission to the load ZL. So this is the transmission line. So here we are interested in finding out the impedance at any point, say at this point. So we need to have a proper notation. So any point is taken as the load end. So we in this, from now on, whenever we say at any point on transmission line, we mean that the point is taken considering the load as the reference. Okay, so at the load end of the transmission line, the L will be equal to 0. So if you want to measure, say, transmission line impedance at, say, L is equal to 0.5, it means we are interested in finding out the impedance 0.5 meter from the load end, that is from here. Okay, so in the previous equations the x was in this direction. Okay, so L is opposite of x. So in order to find out the new transmission line equations, we need to replace x by minus L. Then we'll get the new transmission line equations. So through that we can find the impedance at any point on transmission line. So that point is measured from the load end of the transmission line and not from the generator n. Okay, so I hope this is clear. So let's see the new transmission line equations. So put x equal to minus L, then this will be equal to v plus e raised to gamma L plus v minus e raised to minus gamma L. Okay, and I will be equal to v plus upon z naught e raised to gamma L minus v minus upon z naught e raised to minus gamma L. So these are our new transmission line equations. So you wipe out this from your mind. So these are the two very important equations. We'll be needing this equations in the further study of transmission lines. Okay, so this is VL and IL. Okay, if you want to find out the transmission, what is the voltage at any point L, just substitute the value of L, say 0.5 meter or 0.8 meter from the load end, then you will get the corresponding equation of voltage and current. So then we'll see what is the impedance using these two equations. Okay, and then we'll see the characteristic of that. Then eventually we'll go to quarter wave transformer. So from the transmission line equations, it is clear that there is a forward traveling wave, and there is a reflected wave. So it is important for us to investigate how this load impedance ZL contributes to the reflected wave. Okay, so before we do that, let's define a parameter which will give us the relative amplitude of two waves at any point on the line. Okay, so that parameter is called as reflection coefficient of a transmission line. So it is denoted by this. Okay, and it is defined as follows. Okay, this is v raised to minus gamma L upon v plus e raised to gamma L. Okay, so this is just a ratio of reflected wave to the forward traveling wave, that is called as reflection coefficient. Okay, so substituting this into the main equation, we can further write it as this, e raised to minus 2 gamma L. Okay, so we can substitute this value, that is reflection coefficient, and the two transmission line equation, then we'll get the equations as follows. Okay, this will be v of L equal to v plus e raised to gamma L 1 plus, and current will be v plus upon z naught e raised to gamma L 1 minus this. Okay, so the impedance at any point on the line then will be, this will be impedance at any point on the line. This will be equal to ratio of v of L to I of L. So that will be Z of L equal to z naught 1 plus 1 minus. Okay, so inverting this equation, we can find the value of reflection coefficient in terms of impedance only. So that will be, reflection coefficient will be ZL minus Z naught upon ZL up plus Z naught. Okay, so this is an important parameter. So for any transmission line, the value of this should be approximately equal to 0. Okay, so if there is no reflection from the load end, it means the reflection coefficient is equal to 0. Okay, so now without losing the generality, let us take the load end of the line as the reference point as we did earlier. Okay, we'll take this as the reference point. So then at L equal to 0, that is at this point, ZL will be equal to Z of L will be equal to ZL. Okay, that is this impedance. Then our new equation will be, that is reflection at L equal to 0 will be equal to OL. Okay, this will be ZL minus Z0 upon ZL plus Z0. Okay, so this term is called as reflection coefficient at the load end. So these are all the few parameters which you need to know. Okay, so these are the parameters which define the transmission line. So this is the reflection coefficient in terms of impedance. Now what we'll do, we'll find out the voltage and current at any location on transmission line. That is the final two equations in terms of reflection coefficient at the load end. Okay, so let me summarize what we did till now. So first we learned that the notation, okay, how the impedance at any point on the transmission line is calculated. So it is calculated from the load end of the transmission line. Okay, so we changed x equal to, we substituted x is equal to minus L in the original transmission line equations. So we got the new equations for voltage and current. And also we learnt that there is a forward traveling wave and there is a reflected wave. So the value of impedance, the load impedance ZL will contribute to the reflected wave. Okay, so then we define the term called as reflection coefficient, which is the ratio of the reflected wave to the forward traveling wave. Okay, so then we found out that the reflection coefficient at the load end of the transmission line, that is for L equal to 0, the value will be ZL minus Z0 on ZL plus Z0. So if ZL is equal to Z0, then there will be no reflection. Okay, there will be only forward traveling wave. Okay, so then after defining this term, we got the new equations, that is modified versions of the original transmission line equations. So using all those terms, the final equation to find the impedance at any point of transmission line will be as follows, that is Z of L, where L is measured from the load end, will be equal to characteristic impedance Z0 into 1 plus this reflection coefficient e raised to minus 2 gamma L upon 1 minus tau L e raised to minus 2 gamma L. So where this is called as reflection coefficient at the load end. Okay, let me write it here. This is reflection voltage at the, this will be equal to V minus upon V plus. Okay, this is the reflected voltage at the load end and incident voltage at the load end. Okay, so this equation is very important for us in order to understand the working of quarter wave transformer, because we need to find the impedance and all that. So I thought, let me explain how to find out the impedance at any point of transmission line. So this is the one part of the video. Okay, and now the second point will be using this equation for a lossless transmission line. Okay, so the next part 1 is completed. Now part 2 will be to understand what is lossless transmission line, and then part 3 will be the quarter wave transformer, working of quarter wave transformer. So since this is taking longer than expected, I'll make two videos out of this. Okay, so thanks for watching. Just was the next part in the another video. Okay, so kindly subscribe to our channel, and if you have any doubts, please use the comment section.